So last time we started off our discussion of geometric sequences, and just to recall, the difference between a geometric sequence and an arithmetic sequence is when we have an arithmetic sequence, we're adding a constant each time. So in this one, we're adding 3 with each iteration as we go down the sequence. With a geometric sequence, we're multiplying. So instead of a D, we have a common ratio of R. So the definition of a geometric sequence is a sequence in which there exists some number R called the common ratio such that A sub n, so A sub n again is some number, any number within the sequence, is equal to that ratio times the number before it. So A sub n minus 1 for n greater than 1. Let's take a look at an example of a geometric sequence which relates to something that we've already talked about. So last time we talked about this football player. So this football player has 2 options for his salary. He could choose plan number 1, which is an arithmetic sequence, in which he gets $10,000 for the first game, and then he gets a $10,000 raise for each game thereafter for 18 games. Or he could choose a plan which would be a geometric sequence. He gets $2 for the first game, and then his salary doubles for each game thereafter. In other words, his first initial salary for the first game is A sub 1, $2. And then it doubles after that. So in this case, our ratio is also 2 because it's doubling. So let's look at what that would be for each of the successive games. So he gets $2 in the first game. That's our A sub 1. Then those $2 doubles. So that's A sub 1 times our ratio. Then that salary doubles. So it's 2 times the ratio again. In other words, 2 times 2 squared. So that's our A sub 1 times the ratio squared. Then we take that previous number and we're going to multiply the ratio again. So I have 2 times 2 squared, but I'm going to double it again. So in other words, this is 2 times 2 cubed, or the first number times the ratio cubed. Then to get the fifth term, I take the previous term, 2 times 2 cubed, and I double it again by multiplying by 2. So then this becomes 2 times 2 to the 4th power. So my fifth term is the first number times the ratio to the 4th power. To get my sixth term, I take 2 times 2 to the 4th power, my previous term, and I double it again. So this is 2 times 2 to the 5th power, 64. So I'm taking my initial term, multiplying it by the ratio to the 5th power to get my 6th term. To get my 7th term, I take 2 times 2 to the 5th power and I double it. In other words, this is 2 times 2 to the 6th power, 128. So I take my initial term and I multiply it by my ratio raised to the 6th power to get my 7th term. So here we're seeing a pattern, okay, I take my initial number, my first number, right, a sub 1, and I multiply it by my common ratio, and I raise it to the n minus 1 power. So in order to get my 18th term, I'm going to plug in 18 in for n. So in this sequence, my general term is going to be a sub n is equal to my first term, 2, times my r is 2, raised to the n minus 1. So to get my 18th term, I do 2 times 2 to the 18 minus 1 is 17. Okay, so then I get a sub n is equal to a sub 1 times r to the n minus 1. That might be a lot to take in, but this is just to show you what the sequence is and how I get the general formula for a geometric sequence. Because this sequence, or this general formula, is the recursive. In other words, I'm finding out what the next term is based on the previous term. This general formula for a geometric sequence will be able to give me any term that's in the sequence. So again, rather than a constant difference as in an arithmetic sequence, there's a constant percent change, which we call r, or the common ratio. The nth term of a geometric sequence is given by this general formula. A sub n is equal to a sub 1 times r raised to the n minus 1 power. Let's look at some examples here. So when I go from 1 to 3, what do I multiply by in order to get 3? I'm going to multiply by 3. To get from 3 to 9, I'm going to multiply by 3. So my common ratio is 3. So my next 3 terms for this sequence is 27, then multiply by 3 again, and I get 81, multiply by 3 again, and I get 243. So my a sub n is equal to my first term, 1, times my ratio, 3, raised to the n minus 1 power. And I can simplify this because anything times 1 is itself. Okay, the second one is descending, but you still want to ask the question, what am I multiplying by in order to get my next term in the sequence? So if you're looking at 64 to 16, you might be tempted to say I'm subtracting or dividing, but I want you to think it in terms of multiplication. So you could say, okay, 16 divided by 64 will help me get this ratio, okay? That's equal to 1/4. But I want you to think, to go from 64 to 16, I multiply by 1/4. Okay, the iPad went out on me, so I need to just kind of catch up here. So then you're going to think in terms of multiplying by 1/4 with each iteration. So my common ratio is 1/4. So my next 3 terms will be 1, 1/4, and 1/8. So my general term will be a sub n is equal to a sub 1, which is 64, times my ratio 1/4 raised to the n minus 1 power. Then for part C, I am multiplying by -2 with each iteration of the sequence. So my common ratio is -2. My next 3 terms then would be 8 times -2 is 16, then 32, then negative 64. And my general formula would be a sub n is equal to 2 times negative 2 raised to the n minus 1 power. So what does this look like? What does a geometric sequence look like in real life? Well, compounded interest is a geometric sequence because when I make an investment, let's say of $1,000 over some fixed number of years, let's say 3 years, in some, maybe it's a mutual fund or something like that, and I receive a 6% interest compounded annually. What that means is I'm getting interest upon interest. So I'm not increasing my investment by a constant rate, but rather by a geometric rate, okay? By some ratio each year. Compounded interest can be calculated by some interest formula. This is the one that's in your book. This one's probably a little bit easier to understand. So my sum is the original principal, or my initial amount, okay, my original investment, multiplied by 1 plus my interest rate raised to the power of t, which is my years. So let's break down what this looks like. My year 0, okay, right here, I have $1,000. The next year, by the end of year 1, I'm going to add 6% of 1,000 to that original amount. So I'm taking my principal investment, and it's going to be increased by 6% of that principal investment. If I were to factor out 1,000, this would be equal to 1,000 times 1 plus 0.06. So the general formula for this particular situation then would be 1,000 times 1 plus 0.06 is 1.06. And then I raise that to the time t, which in this case, I'm in the first year, t1. So after my first year, I'm going to get $1,060. Then year 2, I take my original 1,000 plus 1 plus my interest rate raised to the second power. So year 2, I get $1,123.60, excuse me. Then year 3, I do the same thing, except it's raised to the third power. So then that's $1,191.02. So is this a geometric sequence? Yes. What's my R? 1.06. Okay, so this is what I'm increasing by. What would be the value of my investment in n years? Okay, it would be S is equal to 1,000 times 1.06 raised to the nth power. In 25 years, it would be 1,000 times 1.06 raised to the 25th power. So $4,291.87. Okay, let's say I have a car, a $50,000 car, and it depreciates in value as soon as I drive it off the lot. It's going to depreciate by 20% of its original value each year. So over the course of the first 5 years, it starts off as 50,000. After the first year, it's 40,000. Okay. After the second year, it's depreciating by 20%. So I take 40,000 and subtract 40,000 by 20%, which is point. So I have 40,000 minus 40,000 times 20% is 0.2. So that's 32,000. Okay, now I'm in year 3. So let's go to year 4. I have 32,000 and it depreciates by 20% of 32,000. Okay, 25,600. Okay. Then that last year, it's going to depreciate by 20% of 25,600. So I have 25,600 minus 25,600 times 20%. So 20,480. By the end of the third year, so this is the initial value, end of the first year, end of the second year, end of the third year. That car is worth $25,600. By the end of the nth year, okay, remember, I'm taking $50,000 and I'm subtracting $50,000 times 0.20 raised to the nth power. Okay, so then this would be like saying $50,000 minus 0.2 raised to the nth power, which is $50,000 times 0.80 raised to the nth power. Okay. Okay, we're almost there. All right, bacteria. This is increasing by 20%. So my R is equal to 1.20 because I'm increasing. If it were just 0.20, I would be decreasing. Okay, then my A sub 1 is my 2,000 bacterium in my original sample. How many will be present at the end of 10 hours? Okay, so I start off again with 2,000 bacteria. I'm going to add 2,000 bacteria plus 20% of 2,000. So 2,000, if I factor out my 2,000, I have 1 plus 0.20. So then this is 2,000 times 1.20 raised to the 10th power, which is equal to a really big number, 12,383.47. Okay. All right, I have a little video. So that's the end of geometric sequence. This video deals with rabbits, the Fibonacci sequence, okay? And basically what the video explains is Fibonacci came up with this sequence assuming that rabbits never die, they always produce a male and a female, and they mature and are ready to reproduce after 1 month of being born. So if I have a pair of rabbits and they're just born, I have 1 pair of rabbits. Then after the first month, so now I'm in month 2, they are ready to mate. So here's my pair of rabbits. So I still only have one pair of rabbits. They have a pair of rabbits, a boy and a girl. So now in month 3, I have my original pair of rabbits and then a baby pair of rabbits. So I have 2 pairs of rabbits. Okay? After month 4, this pair of rabbits still exists, but then they had another pair of rabbits. But they're babies. However, this pair of rabbits are now adult and mature. So after month 4, I have 3 pair of rabbits. Okay. In month 5, okay, this pair of rabbits has another pair of rabbits. The original pair has another pair of rabbits. This pair can't have rabbits yet. They're not mature, but they're about to be. And then this pair of rabbits, they still exist. Okay. And they have another pair of rabbits. So now I have 5 pairs of rabbits in month 5. 1, 2, 3, 4, 5. Yeah. Then in month 6, my original pair of rabbits has a pair of rabbits. Their pair of rabbits have matured. They still exist. They have another pair of rabbits. Okay. Then my other pair of rabbits that have matured have another pair of rabbits. Then my third pair of rabbits that has matured has another pair of rabbits. And then those pair of rabbits still exist. So then I have 8 pairs of rabbits in month 6. This forms a Fibonacci sequence, okay, where I start off with 1, then I have 1, then I have 2, then I have 3, then I have 5, then I have 8. So instead of increasing by a constant ratio, I am taking 1 and 1, adding them together, and I get 2. Then I take 1 and 2, add them together, and I get 3. Then I take 2 and 3, add them together, I get 5. 3 and 5, add them together, and I get 8. This is the Fibonacci sequence. So what would be the number of rabbits for the next 4 months? I take 5 and 8, add them together, I get 13. 13 and 8, add them together, 21. 13 and 21, add them together, and I get 34. 21 and 34, add them together, and I get 55. Okay, that is the end of this lesson on sequences. Next time we will talk about series. A series, again, are sequences where you just add up the elements of the sequence. Okay, I just want to say one more word about this homework assignment. The one on arithmetic sequences, it's assignment number 5. A couple of things. There was a little bit of confusion for number 11. So the difference between number 9 and number 11 is that the common difference D is 15 for number 9, and the common difference D for number 11 is negative 15. And then the next thing I want to just kind of emphasize, for number 14, you don't need to know what the starting salary is. That's irrelevant to the question because it's asking how much more you would be making after the 8th year. Or by your 8th year. So you're taking the $1,500, right? And you're multiplying it by 8 minus 1. Okay, so that's the course of 7 years total, right? Because it's after the 8th year. So that's what you're doing for number 14. And then finally, for number 15, there was a little bit of confusion on that. And it's this. Straight line depreciation means that this car is $35,000, and by the end of 5 years, it's going to be worth nothing. So you want to take $35,000 and divide it by 5, which is $7,000, and that is what your D is. It's depreciating in value by $7,000 so that by year 5, that car isn't worth anything. I think that takes care of most of the questions from the homework for this week. And I'm signing off. I hope you have a great day.